For most of human history, we imagine the universe as a grand ocean. Vast, yes, but evenly filled. Stars scattered like islands, galaxies flowing smoothly through space, energy humming everywhere. Modern astronomy inherited this intuition. Even as telescopes grew stronger and equations sharper, the underlying assumption remained the same. Space may be empty of air, but it is never truly empty of something. On Earth, emptiness is rare. Even the deepest vacuum chambers contain particles. Even silence carries vibration. So when humans looked outward, they expected the universe to behave similarly. Matter here, radiation there, a predictable balance across unimaginable distances. This belief quietly shaped cosmology for decades. But the universe does not respect human intuition. As instruments launched by NASA and the European Space Agency began mapping the cosmos with unprecedented precision, a troubling pattern emerged. The universe was not evenly filled. It was uneven, lumpy, fractured. Regions of dense galaxy clusters existed alongside expanses so empty they defied expectation. Then came the shock. Scientists identified an enormous region of space that was not merely sparse, but abnormally so. Colder than surrounding space. Devoid of galaxies on a massive scale. Quiet in a way that physics struggles to explain. Against the faint afterglow of the Big Bang, this region appeared as a scar, a dip in temperature and structure where something should have been. This was not a poetic metaphor. It was a measurable anomaly, detected independently by multiple satellites, verified across years of observation. A place where the universe seemed to thin out, as if reality itself hesitated to exist there. The discovery forced an uncomfortable realization. The cosmos is not a smooth, balanced system. It contains voids so vast and cold that even the background radiation of creation grows weaker. And if such a silence can exist on the largest scales imaginable, then our assumptions about what fills the universe, and why, may be far less secure than we once believed. To understand how scientists can find a place where almost nothing exists, we first need to understand the faintest signal ever measured by humanity: the cosmic microwave background radiation. Cosmic background radiation is not light from stars or galaxies. It is far older. It is the leftover heat from the moment the universe became transparent, roughly 380,000 years after the Big Bang. Before that time, the universe was a dense, opaque plasma. Light could not travel freely. When the universe cooled enough for atoms to form, radiation was released in every direction at once. That radiation has been stretching and cooling ever since, filling the universe like a ghostly afterimage of creation itself. Today, this radiation is extremely cold, just 2.725 degrees above absolute zero. It is also remarkably uniform. In every direction, it appears nearly the same. Nearly, but not perfectly. Tiny variations in temperature exist, differences measured in millionths of a degree. These imperfections are not noise. They are information. They reveal how matter was distributed in the early universe and how large-scale structures formed over billions of years. Mapping these variations requires instruments beyond Earth's atmosphere. This is where NASA and the European Space Agency enter the picture. NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, was launched in 2001. Its mission was simple in concept and brutal in execution: measure temperature differences in the cosmic background radiation with extreme precision across the entire sky. WMAP spent 9 years scanning the universe, gradually building a full sky map that transformed cosmology from theory-heavy to data-driven. ESA followed with the Planck spacecraft, launched in 2009. Planck pushed sensitivity even further. It measured not only temperature differences but also polarization patterns in the background radiation. This allowed scientists to separate genuine cosmic signals from foreground interference such as dust within our own galaxy. Where WMAP revealed the structure, Planck sharpened the edges. Using these maps, scientists analyzed statistical uniformity. The universe, according to the standard cosmological model, should display random but evenly distributed fluctuations. When a region deviates too strongly from these expectations, it stands out. This is how cold spots are detected. They are not holes or gaps seen through a telescope. They are regions where the background radiation is measurably colder than predicted, extending across enormous angular sizes in the sky. The temperature difference is small, but the scale is vast, spanning hundreds of millions to billions of light years. The physics is straightforward, even if the implications are not. Less matter along a line of sight means photons lose less energy while traveling, creating subtle temperature distortions. Massive voids can imprint these signatures. But when the size and depth of a cold region exceeds statistical probability, scientists must confront an unsettling possibility. Either our models are incomplete, or the universe contains structures far stranger than expected. In this way, space agencies do not merely map stars and galaxies. They map absence. They chart the shape of nothing, using the oldest light in existence as their guide. Among the countless data points etched into maps of the cosmic microwave background, one feature refuses to fade into statistical background noise. It is known simply as the cold spot. Unlike ordinary fluctuations scattered randomly across the sky, this region stands out by its size, depth, and persistence across multiple observations. The cold spot appears as an unusually large area of lower than average temperature in the cosmic background radiation. It spans roughly 5 degrees of the sky, an enormous patch by cosmological standards. To put that into perspective, the full moon covers only about half a degree. Whatever caused this anomaly left an imprint on the universe that stretches across billions of light years. The temperature difference itself sounds deceptively small. The cosmic microwave background averages about 2.725 Kelvin. The cold spot is only about 150 microkelvin colder than that. This difference is less than 1/10,000th of a degree. On Earth, such a variation would be meaningless. In cosmology, it is profound. At this scale, even tiny deviations signal events or structures of immense size and mass. According to the standard model of cosmology, temperature variations in the cosmic background should be random and statistically uniform. Small hot and cold spots are expected, but their sizes and intensities follow predictable patterns. The cold spot breaks those expectations. It is too large and too cold to be easily dismissed as a random fluctuation. Statistical analyses show that the probability of such a feature occurring by chance is low enough to demand serious attention. This is where the anomaly becomes unsettling. The cold spot was first detected by NASA's WMAP mission. At the time, scientists considered the possibility of data contamination or instrument error. But science is unforgiving to convenient explanations. When the European Space Agency's Planck satellite later mapped the same region with higher resolution and different instrumentation, the cold spot remained. Independent analysis confirmed its existence. It was not a glitch. It was not a foreground artifact from our own galaxy. It was embedded in the fabric of the cosmic background itself. Further confirmation came from cross-checks using different frequencies, polarization data, and statistical methods. Each approach reinforced the same conclusion: the cold spot is real. What makes this region especially disturbing is not just its temperature, but its scale relative to cosmic uniformity. The early universe was remarkably smooth. That smoothness is the reason galaxies formed in the first place. A deviation of this magnitude suggests either an enormous structure affecting the path of ancient photons or a feature imprinted during the universe's earliest moments, before galaxies even existed. Scientists have proposed explanations ranging from a massive supervoid along our line of sight to more exotic possibilities involving early universe physics. None fully resolve the anomaly without stretching existing models. The cold spot remains an outlier, a measurable region where the universe does not behave as expected. It is a reminder that even the oldest light in existence carries unanswered questions. And sometimes, the most unsettling discoveries are not violent or bright, but cold, silent, and stubbornly real. In cosmology, emptiness is not an accident. It is a structure. As astronomers mapped the large-scale distribution of galaxies, they discovered that matter in the universe does not spread evenly. Instead, it forms a vast cosmic web. Galaxies cluster along filaments and walls, surrounding enormous regions where very little exists. These regions are known as voids. Some are relatively small, spanning tens of millions of light years. Others are so large they challenge the scale at which structure itself is supposed to form. These largest known voids are called supervoids. A supervoid is not an absolute vacuum. It is not a hole in space. Rather, it is a region where matter density is far lower than the cosmic average. Fewer galaxies, less dark matter, less gravitational influence. In a universe governed by gravity, this absence matters just as much as presence. One of the most studied examples is the Eridanus supervoid, a colossal region aligned with the location of the cosmic microwave background cold spot. Estimates place its diameter at roughly 1 to 2 billion light-years. Within this volume, the number of galaxies is significantly lower than expected. Entire clusters that should exist, statistically speaking, simply do not. This absence has measurable consequences. As ancient photons from the cosmic background radiation travel through space, gravity subtly alters their energy. When photons pass through dense regions, they lose energy climbing out of gravitational wells. When they pass through underdense regions, they gain some energy back. In extremely large voids, this balance can be disturbed. The result is a temperature imprint on the cosmic background, a cold or hot region depending on the structure encountered. In the case of a supervoid, the lack of matter means photons experience a net energy loss over time due to the expansion of the universe overpowering gravitational effects. This phenomenon, known as the integrated Sachs-Wolf effect, provides a physical mechanism linking large voids to cold regions in the cosmic background. Yet even with this explanation, the scale remains troubling. To fully account for the observed cold spot, the Eridanus supervoid would need to be unusually large, unusually empty, or both. Observational surveys using galaxy redshift data confirm a significant underdensity, but whether it is sufficient remains debated. The void exists. Its extremity is the question. This leads to a deeper issue. What does nothing actually mean in astrophysics? Nothing does not mean zero. It means below expectation. Fewer particles per cubic meter, weaker gravitational pull, less influence on passing radiation. In deep cosmic voids, there may be only a few atoms per cubic meter compared to thousands elsewhere. Dark matter density drops. Galaxy formation slows or halts entirely. From a human perspective, this is still something. From a cosmic perspective, it is an absence large enough to shape the universe's oldest light. Supervoids reveal that emptiness is not passive. It leaves fingerprints. It bends statistics. It alters radiation. And when emptiness reaches the scale of billions of light years, it stops being a background feature and becomes a problem physics must explain. Modern cosmology is built on a model that works remarkably well. Known as the lambda, cold dark matter model, it explains the expansion of the universe, the formation of galaxies, and the pattern of temperature fluctuations in the cosmic microwave background with impressive accuracy. Most observations fit its predictions within narrow margins of error. That is precisely why anomalies like the cold spot create unease. The problem is not that the model fails completely. It is that it does not fail where it should. Within this framework, large voids are expected and small temperature fluctuations are normal. But when both combine at an extreme scale, the explanations begin to strain. The cold spot is not easily dismissed as noise, yet it does not sit comfortably within standard expectations either. It occupies an awkward middle ground where physics hesitates. One proposed explanation is the simplest: a large-scale void. If a massive supervoid lies along our line of sight, it could imprint a cold region onto the cosmic background through known gravitational effects. This idea is grounded in established physics and supported by galaxy surveys. However, modeling shows that even an unusually large void struggles to produce a temperature dip as deep and wide as the one observed. To make the numbers work, the void must be exceptionally empty or improbably large. That leads to the second possibility, an anomaly rooted in the early universe itself. In this scenario, the cold spot is not caused by structures that formed later, but by irregularities present during the universe's earliest moments. Subtle deviations during cosmic inflation, a brief period of rapid expansion, could have left lasting imprints in the background radiation. These ideas remain speculative but mathematically plausible. The challenge is that inflation models are flexible. With enough parameters, almost any anomaly can be explained after the fact. That flexibility weakens confidence rather than strengthening it. The third explanation is statistical improbability. The universe is vast, and rare events do occur. Some scientists argue that the cold spot is simply an extreme but ultimately random fluctuation, the tail end of a probability distribution. In this view, its existence does not demand new physics, only patience and restraint. Yet this explanation is emotionally unsatisfying. When independent missions detect the same feature, and when its scale pushes the boundaries of expectation, randomness begins to feel like avoidance rather than resolution. What makes scientists uneasy is not the lack of ideas, but the lack of closure. Each explanation partially works and partially fails. None can be confirmed decisively. None can be ruled out cleanly. Notably, there is no serious scientific support for exotic interpretations involving extraterrestrial intelligence or artificial structures. The data does not require such leaps, and professional cosmology resists them. The discomfort here is quieter and more profound. It comes from realizing that a well-tested model may still be incomplete, not catastrophically wrong, but subtly insufficient. The cold spot does not shout. It whispers. It sits in the data, unchanged by better instruments or sharper analysis, reminding scientists that even with precise measurements and elegant equations, the universe still contains regions that do not fully explain themselves. For much of modern cosmology, symmetry has been a comforting assumption. On the largest scales, the universe was thought to look essentially the same in every direction. This principle, known as cosmic isotropy, underpins many of the equations used to describe space, time, and matter. It allows scientists to treat the universe as a balanced system rather than a chaotic one. The cold spot challenges that comfort. If regions of space can deviate so strongly from expected uniformity, then symmetry may be an approximation rather than a rule. The universe may be broadly consistent, but locally distorted in ways that matter over vast distances. A structure large enough to affect the oldest light in existence suggests that large-scale balance is more fragile than once believed. This possibility opens an unsettling door. If matter distribution can vary dramatically, then the physical conditions tied to that distribution may vary as well. Gravity, expansion rate, and the behavior of radiation are all influenced by large-scale structure. While fundamental constants appear stable when measured locally, subtle differences across cosmic scales are not entirely ruled out. Even a slight variation, stretched across billions of light-years, could reshape how galaxies form or how energy moves through space. These are not dramatic violations of physics. They are quiet shifts, the kind that accumulate over time. A universe with uneven structure is still governed by laws, but those laws may express themselves differently depending on location. Predictability becomes statistical rather than absolute. Against this backdrop, Earth's position begins to look less ordinary. Our region of the universe appears relatively smooth, rich in galaxies, and dynamically stable. This stability allowed stars to form in steady cycles, heavy elements to accumulate, and planetary systems to persist long enough for life to emerge. If immense voids and anomalies represent extreme environments, then our location may sit in a comparatively gentle pocket of cosmic history. This does not imply design or intention. It implies rarity. Stability, in this view, is not guaranteed. It is a local condition. Just as galaxies can cluster or vanish depending on their surroundings, so too can the long-term prospects of complex structures. A slight change in large-scale conditions could mean fewer stars, weaker gravitational binding, or harsher radiation environments. The cold spot and the void associated with it suggest that the universe contains regions where structure barely formed at all. Places where matter thinned, cooled, and drifted apart before complexity could take hold. These regions are not hostile in an active sense. They are indifferent, empty, silent. The darker implication is not that the universe is dangerous, but that it is uneven. Humanity exists within a narrow band of conditions that permit persistence. Beyond that band lie vast expanses where the same physical laws produce emptiness instead of worlds. In that context, our existence resembles a fragile bubble, suspended within a much larger, quieter reality. A small island of structure surrounded not by chaos, but by absence. And absence, on cosmic scales, does not need to act. It only needs to continue. The cold spot and the vast void aligned with it do not announce themselves with violence or light. They exist without drama, without motion, without urgency. And yet, they remain, measured, confirmed, and unresolved. The universe allowed this region to exist. Through billions of years of expansion, through the formation of galaxies and the ignition of stars, this immense absence endured. It was not erased by gravity. It was not smoothed out by time. It remained large enough, empty enough, and cold enough to leave a permanent mark on the oldest light in existence. Whatever processes shaped the universe did not correct it. They accommodated it. That fact alone is unsettling. Science excels at explaining patterns. It thrives on repetition and predictability. When a structure appears that resists classification, the honest response is not invention, but restraint. In the case of the cold spot, restraint has left a space where answers should be. A space filled only with competing models, partial explanations, and statistical discomfort. We do not know whether this void is the result of an extreme fluctuation, a relic of the universe's earliest moments, or a sign that large-scale structure is more variable than assumed. Each possibility fits the data imperfectly. None can be confirmed decisively. The universe has not provided a clear verdict. And perhaps it will not. The cold spot does not threaten Earth. It does not approach. It does not change. Its influence is already complete, etched into radiation that has traveled for nearly 14 billion years to reach us. All that remains is the implication that the universe is capable of sustaining regions that defy our expectations indefinitely. There is no final revelation waiting beyond this observation. No dramatic conclusion, only a measured silence, recorded in microkelvin and probability curves. As our instruments improve and our models refine, the void remains where it is. Quiet, empty, unexplained. And in that silence, the universe offers no reassurance.